Now, which means you have a random process to classify. Now, if you need to make the classification about the random process, that means that you have a vector of that random process. So you have just a realization of that random process. Now, this vector might need to classify if, for instance, the observation is a signal plus noise or noise only. Now, about the signal, I don't know the signal. I know its covariance. Now, let's make an example. Suppose that, I have an intelligent system, okay, which is trying to detect if within a certain noise there is someone that is speaking. Okay. So if there is someone that is speaking, the speech is different from the background noise. So the background noise, I don't know, it might be white noise. Have you ever heard of white noise? It's like, okay. Now, so if you listen to white noise, if you listen to noise when it's low pass, you get something like this one, okay? Make experience on that, So you have a map, so it's like sound, blah blah, okay? So do it. So the case of the noise, whatever it is, low pass, wide, high pass, and so on, okay? It has a certain covariance matrix. So I can say that that piece of observation, so with this piece of observation is a vector which has a specified length, n samples. So these n samples is a realization of the noise only. Then in that case, the covariance matrix is the covariance matrix of the noise. Or it is the signal plus noise, where I don't know, the signal is a speech, okay? So just to imagine, okay, this one can be speech, okay? Speech, so my goal is to detect the speech versus noise, okay? So I need to detect if there is a speech into the noise, or if it is noise only, okay? So, this might happen, okay? So now, let's assume that about the speech, I know its covariance. Now, how do I know the covariance? Remember that the covariance, if the process is stationary, is just, it contains the autocorrelation along the diagonals, which are striped along the diagonals, so the center diagonals, which is the principal diagonal, then the first upper diagonal, the second upper diagonal. So if the process is stationary, so these CS, okay, contains, we write here, so CS, okay, it contains, a stripe in this way as a stupid structure of autocorrelation RSK, okay? So once I know the autocorrelation, now that means once I know the power spectral density, that means, for instance, if the power spectral density is related to a male, there is a dominance of the lower component, of the lower spectral component. If it is a female, there is a dominance of the high spectral component, okay? So, and by the way, this is due to the oral cavity. The oral cavity for male and female is different, okay? For this reason, the voice in man, he has a dominance of the low frequency component, and the female is the high frequency component. So, I can make a binary decision if it is a male or a female. The voice of a male and the voice of a female, okay? So then, the same problem can be detecting between C1 and C0, where C1 is the covariance for corresponding to the male, and C0 can be the covariance corresponding to the female, okay? Now, how do I get it? How can I make in a training based? Now, in a training based, I can do it because I can record the voice of many males, and then make the power spectral density for that, which is the spectral analysis, okay? You can make it, you can make parametric or non-parametric spectral analysis. Now, in any case, you can calculate the spectral properties. So you can calculate the covariance matrix, okay, in that case, for males. So you have your database of signals for males, and you have your database signals for females. Okay? So you record that, you calculate the two covariances. So, I mean, this video, okay, honestly, I'm thinking to assign this one as the homothermometry. I have two, I am really, honestly, I'm uncertain about the homothermometry, about the three potential ways. One is this one, which means, classify the voice of males and females and recognize the voice of males and females, okay, starting from a training set. The second problem is, the second potential homework is search for a topic that you like, okay? So you are free to choose the topic. And then, we discuss it. So you choose the topic, you make a classification, whatever signals you like, okay? That might be music, that might be instruments and so on. And then we discuss about that. Now, and the third one is to move away from this subject. But let's go to the male and female. So I have my database, okay, from the voice of males. I have my database of the voice of female. Okay. Now this one is the training set. It's a learning. Okay. So in machine learning it's called the learning set. So you take these files. Now what do you do here? I do the spectral analysis. And I make spectral analysis. It's similar here. Okay. Now, out of the spectral analysis, it comes out from this and that. Now, we call this H0 and this is H1. Okay? Now, these are the two different hypotheses. Okay? So, now I make a spectral analysis. From the spectral analysis, I calculate the autocorrelation of, on the case 0 of k, which is an estimate from the training set, and I calculate the spectral properties of the autocorrelation from the training set of the females. Okay? Now, from this one, I calculate the corresponding C0, which is the covariance matrix for the hypothesis 0, which is a male. And I calculate the covariance matrix for the hypothesis C1. Great. Now, so it's practical. Okay, it's all blah blah. See? Now this is something you can do it. My only concern, the only reason I don't give you these as the homework number 3 right now is that I don't know if these databases exist. Because I don't want that you go with a microphone all over. This is possible, but okay. But I want you to interview other people, okay, and then you create your own database. I mean, this may be possible. I mean, if you want it, fine, okay? Now, given that, my goal is to check if a certain vector, so you get a new voice, so you have a person, okay? And so you need to classify if this person is male or female, just from the voice, okay? Which means that if the specific vector, okay, so this guy is measuring the vector, and this is x, okay? So then I want to see if this x belongs to the class H0 or belongs to the class H1, okay? That's my goal. So I can build something like that. Now, so how do I make it? I make in the following way. So I need to decide, it's here. Okay, it's that one, okay. I need to decide these two conditions. So that means that, you know, when I have X, okay, that X can be belonging to the covariance, so belong is assumed to be generated, okay, from a Gaussian process with covariance C1 with covariance C0. Now, for this exercise, for this model that I illustrate here, the class C0 is the class of noise only. The class C1 is a signal plus noise. But you know, if I do the other way, C1 and C0 corresponds to the class of the covariance corresponding to male and female respectively. Now, you know, how do I write, I mean, the log-likelihood ratio test? Now, the log-likelihood ratio test is derived, in this case, by writing the likelihood ratio test. And the likelihood ratio test comes from writing the corresponding distribution. But you know, in this case, I can write it because I mean it's easy. It's you know, it's something that can be done. So writing that and manipulating the formula after doing the logarithmic, so it comes out that the test is given by this quadratic form, which is X transpose. Then there is the inverse of this covariance 0 and the covariance 1 times X. So, you know, my test is obtained in this way. So, you know, the way I should do it is I should take this log-likelihood ratio test and compare. So, if it is larger or lower than the threshold, and I decide that is a man or that is a woman. Okay? So how do I set the threshold? Now, the threshold can be set according to the false alarm probability, which is the classification error probability. Okay? Which is the classification error is, you know, I classify a man as a female, and then I classify a female as a male. Okay? Now, so if I want to know how accurate is my test, what you can do is this. You can take the file, take this big set of files, and then you have a set of files recorded for male, which is H0, and female, which is H1. Okay. You have this big data set. Now, what you do, you cut the data set at a certain point, okay? And what you do, you use this portion of the data set for learning. Learning is a fancy word to say this process, okay? But you know that extracting the autocorrelation, which is the features, extracting the features here is crucial because you need to do the spectral analysis. So, depending at this stage, what kind of assumption you do, you can make a parallelogram. Okay, if you make a parallelogram, means that you implicitly are doing something that is moving average spectral analysis. You can make autoregressive. You can make ARMA. Okay. Now, these are optional. There are additional uncertainty here. You need a heart to make this step, because what is crucial is that, you know, when you get the autoregressive spectra, the ARMA and so on, you know, I mean, extracting this way depends on what is the order that you choose. So, making this step of extracting the features, for this case, where the features are the autocorrelation for the two hypotheses, is that part that is the artisan part, where you put your heart and your capability to pre-process the data. Now, let's move back. So you take your database where you have the huge amount of, voice from male and voice from females, okay? You randomly resort, you need to resort randomly to avoid that in your learning stage, which is when you take this one for training, your learning stage, you are not biasing the choice. Why do I say that? Because, you know, imagine that my database has been built by going to some females who are, playing rugby. Okay, so they have a voice which is very, okay. Then, you know, or you, whatever, okay. You know, I cannot say it because it is recorded. So you can get many possible, okay, many possible way to represent that, okay. Now, so you need to randomly choose in such a way that you don't bias your classifier because you have been choosing as a training set some females that are talking with a voice like this, or males that are talking like, okay. But no, you need to randomize that, okay? So, you take this one as a learning. Now, usually the learning is in the order of 20%. Something more, something less, okay? Now, you know, you take this one. So from here, you choose, you estimate C0, C1, okay, by doing all this procedure. Then you know what you need to do. After doing that, you get the log, you get the log likelihood ratio test, which is that X transpose of QX, okay? So, what you do here, you select gamma, and so for different gamma, okay, for different gamma, which is a threshold, you get the probability for misclassification, okay? So then you decide the optimum gamma for this set, okay? So you choose, so you take this one for the remaining, let me say, 80%, and you make a test. Test means that you change the gamma and you test it. Change gamma and you test it. Change gamma and you test it, okay? Then after that, you choose the gamma that is giving you the best misclassification probability, okay? Where you define your metric according to the problem where you have. So then, that is your classifier. Now, about the choice of gamma that you do in this iterative, so it's not, I'm not writing equation doing that. The only equation that I'm writing is only how is the log likelihood ratio test. Okay? So that's what I need. But after that, it's all practical. Okay? It's all practical. Now, okay, so this is what is written here. Now, so I can manipulate. So you are at the end. This is the last stage. So you understood that we can manipulate our formula. Once you get your equation, which is solving your problem, you can manipulate your formula in order to put the problem and the equation in a way that is more manageable for the problem that you are solving. In some cases, you can manipulate and you can do it. In other cases, it's less convenient. So if you go back and look at what is the RLS, like, I'm jumping from one topic to another. This is the last day. So I'm jumping from one topic to another. What is the RLS? Recursive least square is simply taking, the solution for an optimal problem and solving it in iterative fashion by manipulating the formula. And this manipulation comes from algebra. That's similar here. So I'm doing some manipulation using algebra to give a meaning to the specific equation that I'm doing here. Now, let's move to another aspect. Let's assume now, and by the way, let me go here. By the way, I can have a different classes. So rather than having binary, I can have male coming from Italy, male coming from Iran, male coming from China, female coming from this. Okay, so we can invent different problems. Now, what does it mean big data for me? I don't know for the others, but for me, big data means the following. You understood, again, you are at the last lecture, you understood that the bigger is the data, the lower is the bias. Okay, this should be clear. Okay, we have been singing this concept in all the possible singing notes. Okay, so now if I have a big set, I can use big learning. So if I use a big learning, that means that the big learning is following these steps. Now, but if for instance, if I use a parallelogram and make a spectral analysis on a big data set for the learning part, that means that the spectral analysis comes with a lower bias. So it's better. So that means that this autocorrection comes with a lower variance. These matches come with a lower variance. Okay? So this is the reason why if I have a big data set, I can do everything. Okay? So this is the fundamental reason why the people having a big data set, they can replace some theoretical aspect that we do because our data set is limited by computing the sample estimates. So if you have a big data set, you can avoid to make some theoretical analysis because the data set itself is telling us how to compute some parameters. Okay, so like if you have a limited data set, then you need to find out the algorithm which is squeezing the data at best, and then we calculate, for instance, a mean square error depending on the number of on the length of the data. Okay, and then since I try to tell you that the more data means more cost. When you have a big data, the cost of the data is zero. So if the cost of the data is zero, then the accuracy of the method disappears. So that's why, when you manipulate a huge amount of data, you don't need to be as accurate as manipulating a limited set. So, that's why I refrain to talk about big data myself. Because if you have a large data set, you can calculate some analytical properties rather than analytic by just running the code. And then you get it. Now, but in some application, you have a big data. You have a big data that you can count on. Like, recognize male, female, you have a different big data set of voices and so on. Okay? And this is mostly because I centralize the acquisition. I cannot imagine that the people on YouTube, they have a huge data set and they can do whatever they want. Recognize the people and so on. So recognize the face, recognize the fake news, recognize everything, okay? They can't do it because they have a huge data set that they can train. The training set is very, very accurate. So, now let's move on a slightly different topic, okay? Which is rather as we did for estimation theory, where we started from the estimation of parameters and then we moved into the estimation of the parameter that has some a priori information. So let's do the same here. Now let's assume that we have two classes, okay, PH0 and PH1, and we know the probability, a priori probability for each of the class. I don't know. I know that in my data set there are 70% of males and 30% of females. That's an a priori information. Okay? So, imagine that this analysis is carried out for the students at Polytechnical. So the voice of the students at Polytechnical. Now, wait a minute. If to recognize the voice of the students of Polytechnical, then I look at the a priori information about how many females are, how many males are. Okay? Then I get the number. I don't know. Honestly, I don't know exactly. let me put the number, okay? So let's imagine that the probability of a male is 80%, the probability of females is 20%. Now, how do I put this into my classifier? There should be a way. Now, so this is what about? So let's imagine that we have two classes, and we know the a priori probability of H1 and H0. Okay, remember, male and female. No? And we know, okay, the probability of X given H1 and X given H0. Now, what is the misclassification error, which is the classification, the wrong classification error? Now, the probability of error is the probability that I have the signal that belongs to the decision region R1. Okay. So this one should be read as follows. This is the probability that X belongs to the decision region R0, given that it was generated by H1. Okay. So the true value is H1. Now time the probability that, you know, it is that specific class, which is a priori known, pH0, plus the probability that it belongs to the region R1, which means I decide for the class 1, given that it was H0. Time its probability. Now, so this one is the probability of classification, so the total probability of classification error. So it's not only the probability of classification for H1 or for H0. So the total probability. So this is the total probability that every time I classify one male as a female and then one female as a male. Okay. Now, so my goal is I want to take this and minimize this classification probability. So now if I want to minimize this classification probability and then I manipulate my definition, now I skip, okay, so go to the book, then it comes out that the classification decision is simply the one that is the a posteriori classification decision. So what is the case, So PH1, so P HI given X is the a posteriori probability for the class HI. Okay? Remember, in the past we did that the probability that theta given X, okay, is the a posteriori probability because it is the probability density function for the parameter theta. Given that, I made a measurement. Okay. Now, that's similar. Okay, so I try to make the parallelisms. That's similar. Don't tell me the same. Okay, if you do the oral, don't tell me the same. And so, conceptually, it's similar. So, that one is the probability that a certain observation X belongs to the class HI. Now, what is the classification probability? Well, in binary case, it's stupid. It is, when the posteriori probability is maximum. But I need to compare one class with respect to another because there are only two classes. And so it is when the probability of H1 given X, which means the posteriori probability, is larger for the class 1, is larger with respect to the probability H0, then I decide for H1. So you need to read it this way. If PH1 given X, which means the posteriori probability for the class 1 is larger in equality, is larger than the probability, a posteriori probability for H0, given the same measurement, X, then I decide for H1. Okay? Otherwise, I decide for H0. So if PH1 given X is larger than PH0 given X, then I decide for X belonging to H1. and reverse it, okay? So pH0 given x larger than pH1. Then in this case, I decide that x belongs to the class H0. Okay? Now, but you know, I can use the bias formula, similarly as I did in the past. Okay? This is the bias formula in this case. The bias formula I apply here, okay, is if I want to calculate, you know, the joint probability, the joint probability is pH1x, okay, it is equal to pH1 given x times px. Then I do the same for the others. Then I normalize. Then I get this new condition. The new condition is the following. So I can get the probability of x given h1 divided by the probability of x given h0. Now this one is the Laqueur ratio test. So the Laqueur ratio test is larger or equal than the ratio between the a priori, depending on what class do I choose. So in case of Bayesian classification, I found a way, optimal way, to have a threshold. I don't need to test for it. I have the optimal threshold. I have the optimal Bayesian threshold. See? In the previous pages, I was writing this part, then I say larger or smaller than gamma. Okay. Previously, I was writing Vx given h1, Vx given h0, okay? Then I will say that one is smaller or larger, larger or smaller than gamma. Then I decide for h1 and h0, okay? Now, this gamma, I said, okay, this gamma depends on blah blah, but you know, put a gamma and then check. Okay? So when I say put a gamma and then check means that calculate a ROC curve, receiver operating characteristic curve. Okay? So now you know what I'm saying is, if I have the a priori information about the classes, I know what is the optimal gamma. And the optimal gamma is the ratio between the a priori probabilities. So, you know, good. I mean, this is what my feeling is that, you know, I mean, it's getting better with the Bayesian, okay? Because, I mean, you know some a priori probability about what you are treating. You know some a priori about, I don't know, how many male and female there are, and then you start doing, okay? So if you have a male and female, then, you know, at least you know the statistical properties, like the population in whatever country has, I don't know, 51% of female and 49% of males, okay? And you have the coefficient. Now, if the two classes are the same, like, I don't know, there are the same number of male and female, then in a population of whatever city, then my Laqueur ratio test becomes, you know, that I need to check if this guy is bigger than the other, which is the third on the last line of the slide. Just the bottom here, last one. Okay. Now, let's make an example. So, for instance, you know, if I have two classes, like here, male and female, C0, C1, blah, 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 okay? Then, you know, I mean, if you, and by the way, I know that in my Gaussian distributions, so this is the most general one, so, you know, that means that x is depending on h0 or h1, it has a distribution that is normal with mu0 mean and c0 as a covariance, so normal, with mu1 as a mean and c1 as a covariance. Okay? So in this general case, then I can calculate the optimum classifiers, which is this one. Now, it's quadratic. unfortunately, it is quadratic. Okay, now, yeah, so the decision boundary, okay, in this case is linear in the case of, as in the previous case, so it is linear in the case that the covariants are the same, or quadratic in the other. If I need to decide with more than two classes, then I need to find the classification, and then I can calculate the classification error. Now the classification error is the sum of all the cases where the probability x depends on or belongs to this region Rk, does not belong to the region Rk, given that it was Hk as a cases. This is for, but now, I need to test. The probability of error is, I need to check that this measurement does not belong to the other, which is the probability that does not belong to the other. Okay, given that it was generated here. Actually, that means that I need to test for every measurement with respect to all the other k minus 1. And I need to sum k possibility for that. So it is k times k minus 1. So the complexity of this classification is too much. Okay? The complexity is the comparison is k comparison for non-belonging to k minus 1 decision regions, okay, which has a complexity of the order of k squared. Actually, it is k times k minus 1. Okay, so the complexity is too much. Now, an alternative way is that I can calculate the probability of correct classification, and the probability of correct classification is the probability that I belong to this decision region, given that I was, belonging to that. And so the hypothesis, the specific case. So, in this way, I can redesign my classifier for k classes, for a number of classes that is k bigger than 2. Now, actually, I don't have the slides. There are a couple of comments here that I want to make. One comment is this. When you implement these methods, if you have many classes, you need to check if your metric is bigger than the others. So you need to make the comparison between you and all the others. Now this comparison might be too complex. When the number of classes is very big, this comparison means that you need to check one every time. You need to check one probability with respect to all the others, k minus 1. It might be easier, okay, to check in pair. So to check between two hypotheses at a time. Now, this is a numerical strategy that in some algorithm is implemented. This is what in telecom is called the union bound. Okay. The second comment is this. You need to decide, imagine that I have x here. So you need to decide between the two a posteriori probability. Now, let's take this case. Let's imagine that, I sketch the a posteriori probability, and this one is the probability of h1 given x, and this is the probability of h0 given x. So I represent, okay, along this axis, I assume that x is a scalar. Actually, in practice, it's multidimensional. Let's make it scalar. And then I need to decide, which class is that. Now we know from the theory that I decide H1 when the probability for H1 is larger than H0. Okay? Now, so let's see. Now this means that, let's assume that I take this point. Okay, for this point, the probability for H1 is larger than H0. Okay, so, I decide that this value of x belongs to H1. Fine. Then, I go here. Then I have a point here. So, this is x1, this is x2. Now, if I have x2, then, the probability that x2 depends on the class H1 is, 10%. And the probability that it belongs to H0 is 90%. Then what you do is say, okay, x2 is H2, is H0. Okay? So belongs to class H0. Now, let's put ourselves here. Or let me say in a small interval. Now you have these x3. Now for x3, the probability that depends on H0 is 48%, and the probability that depends H1 is 52%. Now actually, imagine that you need to decide if you make a surgery or not, because that might be a tumor or not. Actually, if the probability that, okay, H1 is a tumor, is a cancer, okay? You are a doctor, you see the RX, you see the resonance, the magnetic resonance, you see all the, all the inspection that you imagine. And so your probability that is, it's really cancer, whatever, is very high. It's 90%, and you make a surgery, so you start cutting. Okay, well, it's not good to be in a class H1, but fortunately for some, it happens. But what about if you need to take a decision between 52% and 48%? Now, what do you do? The theory says it's H1, right? That's what the theory says. But you don't feel confident to decide. So, because we need to find a class H0 and H1. Tumor, no tumor. Okay? Or, black and white. Or male and female. Okay? But you are uncertain to what to decide. And so, what we do with this case? Right. We don't decide. So, we can select a region, okay, where, for instance, according to the corresponding probability and according to the delicacy of the problem that we need to solve, we introduce a new class. The new class is not to decide, which does not exist. See? It does not exist in our theory, okay? Because we have been writing numbers, but what I'm doing is move from the numbers to the reality. And then, in the reality, okay, as your colleague says, we make the no decision class. Now, no decide is a new class. So if I don't decide, what I need to do is I need to put in more experiments. I need to do something more. You see? So not deciding is a class itself. Okay? So it might happen something like that. So you are in a position where you cannot decide. So if you can, you don't decide. If you have to decide, you decide for 52 and 48. Okay? Or the third way is that you don't decide, but you just bring your probability. And this is what in Telecom is called soft decoding. Okay? Soft decoding, you never decide. Bring your own probability on. Okay? At a certain point, you might decide. Okay, so I mean, this is what the telecom, telecom we do. Now, this, just to conclude this part, so just to say that when I say decide or make a decision, making the decision, it depends on the case. So, the decision theory is putting, and the classification theory is putting all the framework, the analytical framework, to put some computation, some error computation in a correct way. But then, I mean, the pragmatism, as it was not me saying no to decide. Okay, it's obvious, huh? So you don't decide. So you introduce a new class. Now, the last topic is the class data. So sometimes you get the data. Okay, so you receive your own data, and so you need to work on the data, okay, in order to understand from the data itself how many classes are there. So you are now trying to understand the data. Okay, so we take our, let me say, training set, and we try to understand our data, how many classes that are distinguishable we can use to make the classification next. Let's make an example of that. Okay? Imagine that in a class, in a room, there are people coming from different countries. Okay? I don't know how many countries are here. So then I collect the words, I collect the speeches from the people, and then I try to understand how many possible classes are in those data. I'm understanding the data. Now, so this is called clustering. And this is called, processing the data to learn from the data the possible distinct class that are in data. Now, this operation is well known in signal processing and is called vector quantization. Now, let me make just a digression about it. What is quantization? Quantize means to describe something with a lower number of entities. Now, imagine that you have a vector x. Now, the vector contains any number, okay? So, this vector select a point in this n-dimensional space. Let's to make it easy, our vector to contain n equal 2. It's only to simplify our reasoning, okay? So, what's happened is that, our samples, okay, are in a plane. And so, what I can do is I have my samples x. So every time I have one x, I have 1 point, 1 point, 1 point, 1 point. 1 point in this two-dimensional space. So, what's happened is that my data are in some way, for whatever is data, okay, are in some way grouping in two major groups. So in signal processing, what you can do is that you can quantize the data, you can quantize the representation of these data. What does it mean then? It means that, I can make two classes in this data, and then, I can elect 1 point, when you write the point as an x, 1 point, okay, which is in the second class, the second group, in such a way that this point is a new one. So this point is represented by mu1, and this point is represented by mu2. Now what I can do, I do the following. I represent any point that is belonging to this area as mu1. So I replace any point which belongs to this area as the point mu1. So that means that I'm doing mapping. Okay? So every time I have x, that depends on the region, it stays on the region 1. Okay? So if x stays on the region 1, then what I do, I substitute with x mu1. If x belongs to the region R2, then I replace x with mu2. No, but this operation is more general. And what I do is that, I make a quantization. So I take the vector x, and I take the quantization of the vector x. And so I assign this one to the mu k, so to the cos mu k, if, there, yeah. So if x belongs to the region Rk. Now, so that means that, in order to represent this set of points, rather than representing each individual point, I represent just mu1 and mu2. Now, of course, there is an error when you do this. Because, this point here is represented by mu2. So, there is an error. Okay? This is not true because, the point mu2 is not representing this x when it belongs to this x, this particular x. Okay? So this term is called this distortion. So that means that whenever I represent the point in this region with the corresponding mu2, then I make a distortion. The distortion here is given by, let's say that this is x. Okay? And this one is the distortion. Okay? This distortion is, is simply the distance between x and mu2. This is an error. Okay? We call distortion. So, where is it coming? Well, this one is coming because this is the quantization of x. Okay? So, this distortion is the distortion when, it is for one specified x. So, the distortion for a specific x, let me write this way, is equal to the distance between x and its quantized value. Now, conventionally, rather than having a distance, because, rather than having a distance, I prefer to have the distance to the square. And so I write a distortion as distortion squared. The distance to the square. Okay. Now, so, the specific point might be here, wherever. Okay? So rather than computing a distortion for one specific x, I compute the mean distortion, which is the mean of the distortion, which is, the expectation of, with respect to x, so any possible value of x, which is x minus qx, and qx is, is the quantized value. So this one is the minimum, this one is the mean square distortion, okay? Because it's the square of the distortion. Now, and this expectation is calculated with respect to the distribution of x. Now, my goal is to find a set of points in such a way that the distortion is minimized. So my goal is to find the point mu1, mu2, mu blah 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 in such a way that the mean square distortion is minimized. Now, what is that? This is done by clustering. So what is a clustering? The clustering is the following. So assume that I have this set. I'll look at that one. Assume that I have this set. This set is a set of data. Okay? And these set of data are different each other. So my goal is to define one representative point. So this representative point of the cluster is the point that every time I take this x and I replace with this point. Okay? So this is the value of the quantized value when they belong to this region. So you know I have a set of different values, and the different values that are represented here, here, and there. And, you know, and what I can do is I can rule, so I can change the position of these representative points, which are the quantized value, in such a way that the corresponding mean square distortion is minimized. Now, so if I make it this way, you know, look, this means that I need to calculate the distance. So distance from here, square plus this square plus this square, you know, so that is too big. Now, so what I can do then? I can change the decision region, and I can move the quantized value in such a way that the distance is minimized, because the distortion depends on the distance. So now, you know, I move these points, you know, like I move these points, point number 1 there, the point number 2 there, the point number 3 there. And then I redefine the decision region. Now, this operation can be carried out, it's called clustering, and it can be carried out by 2 ways, which we described. Now, the method number 1 is called the K-mean clustering. K-mean clustering works in this way, so it's very simple method. I need to understand the data, so I collect the data and I have my data set. I need to understand the features in the data. I need to understand how many classes are in the data. In signal processing, we say, I need to understand the centroid that are representing the data. So, now, how I make it? I start with a set of points, then I calculate the distance, and then what I do, I simply, you know, move at the next iteration to make, in the second step, minimizing the mean square distortion. Now, very simple. It's much simpler than you can imagine. Okay? So, I start from an initial set, okay, which are the centroid, which is the center. Okay? Now, each sample, assign each sample xn that is assigned to the closest centroid. So, you know, I have these 3 points, and these are the decision region. By the way, the decision region is the bisection between the 2 distances. Okay? So it's like here, there.
Professor, sorry, those are set before
these are mu. These are these are here are the position of the point mu1 0. This is mu2 at iteration 0. This is mu3 at iteration 0. You can choose randomly.
And the decision regions are...
The decision region you calculate with respect to the distance, for instance.
So a priori you knew the number of clusters.
That's another point.
That's part of the training?
You start with a certain number, okay, and then you see what is the mean square distortion. Okay, see the metric. So you start with 3, and you calculate the mean square distortion. So you start with 3 values, okay, mu1, mu2, mu3 here. Then you iterate with the k-mean, that is the one that I'm discussing now, and then you come to an equilibrium point, okay? You get a certain mean square distortion. Now, if the mean square distortion is not enough, you increase your number of classes by 1. You increase your number of quantized values by 1, and then you iterate it.
But what's the minimum? For example, we have Kramer bound, we know
No,
to what
we
extent
don't
we have
have
to
it.
increase, but here.
No, there is no camera bound. You might, if you iterate, okay, let's look at this way. Assume that I have a 50 points. Okay? Ideally, if I make the quantization using 50 centroids, I get the minimum.
Yes.
Okay. So, I don't want to use 50. I want to use less. So, that means that the mean square distortion is monotonically decreasing for the number of centroid that I'm going to use. Okay. So, there is a certain point where you stop. Okay. So, perhaps, I don't know, if you have you calculate the mean square distortion after converging to the k-mean. Let me discuss about the k-mean. So I understand it's easy, but let's discuss. Okay. So let me do easy right here. Okay, so then you read it. So I start with this assignment. So the centroid is here, and there. So I take all the points, okay, and then I calculate the distance. When I calculate the distance, I assign, the corresponding point to the corresponding centroid, and then it comes implicitly. So the red lines does not exist, okay. So you make the distance, and then these three belongs to this centroid, because if I calculate this other distance, so this 1, 2, 3 belongs to that, because if I calculate the distance from there, it's bigger. Okay, that's simply that. So what I do is that, after computing this distance, then for this set that I already computed, I calculate the body center for that. Okay, calculate the mean. That means that since I need to calculate the mean for that, I move the centroid on the point which is in the center, as I did here, and then restart again, and I iterate until the point are not more reassigned to any other centroid. Okay, then I stop. So now that means that at every step I can calculate, but the mean square distortion depends on the choice of the cluster centroid that are obtained in literature. Fine, but it depends also on the initialization. So that means that if I initialize randomly, as it is the case, what I expect that the mean square distortion, assigning a certain number of centroid, has a certain value. Okay. Now, so if I, like in this case, if I make a 3 centroid, then what's happened is that, after many iterations, I get a certain value of mean square distortion. Now I reinitialize again with 3 new initial conditions for the centroid. Okay, it comes to another solution, and this other solution might be bigger. Then I initialize again, and I come out with another solution, another mean square centroid that is smaller. Okay, and so on. So there is a certain value. So if I initialize randomly, they might stay in a certain interval. Okay. Now I can take and I can improve, rather than having 3 centroid, I can make 4 centroid. Okay. And then this dispersion is reducing and is going there. Okay. So monotonically increasing number of centroids, this is going to 0, and it goes to 0 when the number of centroids is equal to the number of values. Okay, but this is not what we want to do. So, I mean, we need to decide when to stop. We need to decide when the number of centroids is representative enough to describe the overall number of points. Usually I try to use a number of centroids that is minimum, because I mean, more centroid means more class, means more classification. The classification is for more classes, because I mean, after doing that, okay, you need to operate to make the classification for the new data. Okay, imagine that this operation can be done on a training set. So you take your training set and you start looking by the training set at what the data is telling you. So we are exploring the structure of the data. We are exploring the correlation properties among the data. Now, obviously, if I have 2 dimensions, it's easy because I can see. If I have more dimensions, it's more complicated. So usually, in this kind of problems, you have a very nice graphical tools that are taking the overall ensemble of data and projecting into planes, okay? In order to understand if there is one plane that is opening the set of points of data that you don't know the structure in a better way. Now, this is the concept about the k-mean. Yes, it's here. I remember there was a. Now, in order to calculate analytically, you need to define the new variable. The variable is the variable that is describing if one specific value belongs to one specific centroid. Okay. So this is a pseudocode. I call it pseudocode. Now, the other one. Okay. Now there is some pitfall. Okay, that I was describing. Another pitfall. I forgot. So when I make a random initialization, I might have one centroid that has no value, no sample. Okay, and I might have this is as a degenerate case. So that means that when I go to a point where one of the region has no point, that means that that region has no possibility to change the centroid. It doesn't change because I can change only if, look at here. Okay, so what they did here from here to there is that since these group of values are belonging to this centroid, I moved the centroid to the mean. But what about if I have no point? When I calculate the mean is not changing. Okay, so when there is in a classification, when there is a centroid has no value belonging to that centroid, I have to do something like aggregate, like fuse the centroid. Imagine that I have no samples here, or I put the one sample, I make one centroid that is here, okay, and this centroid has no value. So what does this guy? Nothing. It's not correcting, it's not modifying, it stays there, okay? Because I'm not touching one point that has no value. And so, because this one are not moving, they're not changing. These are the data, they're fixed, okay? So, one possibility is that once this point is getting closer to the other, I fuse this centroid with the other. Okay, so I remove one value. And blah blah blah. So there is a code, there is a MATLAB code that does these kind of analysis. The last one that I wanted to tell you is the one that I try to describe rather than by formula, but by by this, this visualized analysis. We have a set of points, okay, that are here. And then I want to find a way to describe these points by the corresponding centroid. Now, if the points are clustered around here, and a cluster around here, and a cluster around here, that means that if I have a very huge number of points, these huge number of points are clustering where the generation mechanism has the highest probability. So in other words, it is like if these set of values are obtained by a realization of a certain probability density function that I don't know. Now, so that means that there is a certain probability density function. Now, this probability density function, which is not Gaussian because it's I have a block here, block here, block here, is a compound of Gaussians, and this is a Gaussian mixture. So the Gaussian mixture is composition of Gaussian because it's sum of Gaussians. So that means that I have my alphabet based on bells. Okay. Now this is my basic alphabet. So I can make a similar iteration where I simply say that this is the centroid and this is the mean of the Gaussian mixture, and this is the covariance of the Gaussian mixture, which is describing this distribution. Now, if this is the mean and this is the mean and the covariance of the first, this is the mean and the covariance of the second, this is the mean and the covariance of the third. Now, so but the mean here, this mean and this covariance are not really representative of that. Because intuitively, if I want to describe this distribution, now this distribution is tilting this way, so it's dispersed in the other direction. So what we should do, I should move the mean at the body center of those points and make a dispersion that is shaped as if the dispersion of the points belonged to the specific classification. Now, anyway, so this method that I'm trying to describe intuitively is called expectation maximization clustering. Now it's done, it's complicated, the analytical derivation. Intuitive, I would say, is very intuitive. So that means that my distribution is a compound of Gaussians, like here, 1, 2, 3. And now, since my goal is to find these three Gaussians, these three Gaussians, they have the mean corresponding to the centroid, and they have a covariance, which is described with a certain confidence, and they have a covariance that depends on how the points are shaped. If they are elongated, the covariance are, have a certain shape. Okay, the eigenvalues of the corresponding covariance are, very sparse. Or, it's very symmetric. So the iterative procedure is attempting from a random initial condition, similar as a k-mean, to iterate until the distribution here, the three distribution for this case, are behaving in such a way that they describe, they means the three distribution, they describe quite accurately this set of points. Now, in this case, after some iteration, the Bayesian, the expectation maximization clustering stops. So what I'm doing, I'm simply, doing this iterative procedure where, I take, imagine, let's take this point here. And imagine that the previous iteration, was behaving like that. Okay, now what I do is, I use this point. This point stays within this region. This region is the region corresponding to a Gaussian. Since this point stays in this region, then I rotate, so I change my covariance in order to include that point, and then it goes the other way. Here it was better. Okay, and then I rotate this covariance in order, for instance, to include that point. Okay, and then it's an iterative process where I update mean and covariances, and then this is the mixture, and then this is the recomputation. So I need to calculate the probability related to the belonging to one class. So I need to redefine all the theory in order to this new theory in order to take into account about the Gaussian mixture theory, and it's apparently it's complicated, but in implementation it's much more easier than it appears. So just to give you an overview about these two possible techniques. So the K-mean is usually the most implemented, and it's easy to be proved that the expectation maximization is due to two steps. Okay, you can go to section here to see what is the EM method, and so it's a very particular method that he has to treat problems where some of the variables are not completely observable. Okay. This is just to give you the flavor about that. So, anyway, my goal is to, I close here. My goal is to put in Dropbox a couple of exercises about this part, like typical exercises. Okay, for this last part. Perhaps these exercises might not be standalone, but perhaps are linked to other cases, like we touched here. We touched the case for radar targeted detection, or like this problem, which is the sinusoid detection in noise, and but sinusoid detection in noise is used in the periodogram, so and perhaps my question might be related to the periodogram. Okay, so I give you some examples of that, so you can find that. So my goal is to give you a couple of examples, put into Dropbox. I write you a few lines. So I write you an email when I put into Dropbox. I write you when I advertise when I have the homework number 3, okay, which might be between Christmas and New Year, or close to Christmas, so 26 or 27. And okay. If you have a problem about any problem, just write me, even during this vacation. Okay. When do we have the exam?
10.
Friday? Is in February?
January.
When?
10.
10. Okay, so if you have a problem, I'm not sure. I think I'm back at 8. In case you need. Surely I'm back. I'm here on 7. Okay, surely I'm here on 7. In case you have any need, you send me an email. And if your issue is solvable by email, then we solve it. Otherwise, we meet on the 7th. Okay. And what else? That's it. Okay. Thank you. Are you recording that? But the others that are at home, they say, it was a nightmare to understand all that, all this.